Welcome back to the Explainer. Today is going to feel a bit like a two-track day, and that's entirely by design. We've got two distinct halves ahead of us. First up, we're doing a technical build, extending our neural network to handle a completely new kind of problem called regression. Then, for the second half, we are deliberately slowing down. We're going to step back and consolidate everything from Unit 1 quantum mechanics before it gets buried under a mountain of new material. You can see how our agenda perfectly maps to those two tracks. We're starting with the additive technical building blocks, the continuous number problem, mean squared error, running the machine, and those crucial practical pitfalls. Then we transition smoothly into our slower, reflective memory retrieval session, the stakes of quantum unit 1, followed by the postulates, cloning, and coding. All right, let's kick things off with the continuous number problem. To begin our live build, we really need to understand why regression is a fundamentally different beast from what we've been doing so far. Before we even think about formulas, we have to grasp this conceptual pivot. So far, our network has been answering simple yes or no questions. Is this a cat? Is this a dog? That's classification. But today, the network has to answer how much questions. Think about it. Imagine trying to predict a $500,000 house price using an activation function like a sigmoid. Sigmoids can only ever output a number between 0 and 1. If you squash the output artificially like that, the absolute highest price your network could ever predict is $1 single. It's completely broken for this type of problem. You simply cannot predict a continuous house price or tomorrow's exact temperature using an activation function that only spits out a probability. The fix to this absurdity is actually incredibly simple. We switch our output layer to a linear activation. All that means is we apply absolutely no artificial squashing to the final answer. We just pass the raw weighted sum straight through. Keep in mind, our hidden layers are still going to use nonlinear activations like ReLU to learn all those rich, complex patterns in the data. It's only that final output layer that changes, allowing our network to finally spit out any real number, negative or positive, massive or tiny. So how do we handle mean squared error? Because now that our network can spit out literally any real number, we need a brand new way to tell it when it's made a mistake. Cross-entropy loss worked great for probabilities, but it's totally useless here. If a predicted house price is too high or too low, both of those outcomes are wrong. Now, you might be wondering, why not just subtract the prediction from the true target to find the difference? Well, think about what happens if we just average out the differences. A prediction that's $100,000 too high and one that's $100,000 too low would literally just cancel each other out. The network would look at an average error of 0 and think it was perfectly accurate when it's actually failing miserably. To fix this cancellation problem, we use mean squared error to properly measure the pain. Squaring the error is brilliant because it forcefully tells the network to fix its absolute worst predictions first. Just think about the math for a second. An error of 2 becomes 4, right? But an error of 10 blows up to 100. The network is being heavily, disproportionately penalized for being wildly off, pushing it to prioritize fixing those massive mistakes immediately. Plus, as a bonus, the squared function is perfectly smooth and differentiable everywhere, which is exactly the mathematical property we need for backpropagation to work. Let's actually run this regression machine. As we move to the math and see how this builds out, keep one major thing in mind. This is the exact same chain rule engine from our earlier backprop lessons. The only thing that's changed is the starting fuel. We are not building a new machine. We're just feeding it a different loss function. Let's watch the forward pass run with some actual sample numbers. We see our inputs flow through the hidden layer, hit the ReLU activation, and move right into our new linear output layer. Our linear output yields a 1.37 against a true target of 5.0. Squaring that difference gives us a massive squared error loss of over 13. The network is way off target, and this massive loss is exactly what backprop is about to correct. The derivative of our mean squared error serves as the seed of the backprop signal. It's a remarkably simple calculation, just -2 times the true value minus the prediction. That derivative starts the backward flow into the output weights, exact same as we've seen before, cascading down through the network using the same chain rule mechanics you already have internalized. I really want to pause and give this moment some room to breathe, because this zeroes out number right here highlights the famous dying ReLU phenomenon. Notice how in our specific forward pass, this particular hidden neuron output, a 0. Because the derivative of a 0 ReLU output is also 0, it gets a flat 0 gradient now during the backward pass. It effectively dies. It stops all learning on that specific pathway for this training step. It is a very real, well-known phenomenon, and absolutely something you have to watch out for when you're training real regression models. Moving on to metrics and practical pitfalls. We're shifting gears here. moving away from how the machine learns on a granular level to how we actually grade its overall performance. And more importantly, what's going to bite you in the real world? We need a completely different way to answer the question, how good is this model? Traditional accuracy just doesn't transfer to continuous regression. There's literally no such thing as being exactly perfectly right when predicting a continuous number. So instead, we rely on metrics like root mean squared error, which is great because it brings the error back into interpretable original units like dollars or degrees. We can also use mean absolute error, which is much less sensitive to those crazy outliers. Or we look at R squared, which is fantastic because it tells us how much of the target's variance our model actually explains, scaling super nicely from 0 to 1. Now, here are the hard-won lessons. This is what will actually trip you up in practice. Failing to scale your inputs and targets or setting a bad learning rate will cause your regression network's unsquashed linear outputs to just explode into massive NAN, not a number values. Because there's no sigmoid bounding the output anymore, unscaled features ranging from 0 to 100,000 will wildly dominate the gradient and completely shatter your training stability. Always, always standardize or normalize your data. All right, taking a deep breath, let's step into Quantum Unit 1 and talk about the stakes. This is where we transition into the slower, calmer consolidation phase for the second half of today's explainer. We're stepping away from the live build to ensure our foundation is completely rock solid. I want to be really clear about why this revision matters. Everything after this point, teleportation, super dense coding, Bell states, quantum key distribution, it is all built directly on top of these 4 postulates and this notation. If any of these foundational ideas feel even slightly shaky, this is the exact moment to fix them. We cannot build advanced protocols on a weak foundation. Let's do some quick memory retrieval on our Dirac-Brocket notation. This is the mathematical language that lets us actually compute probabilities and overlapping states. The ket is our column vector representing the quantum state. The bra is its conjugate transpose row vector. Smashing them together gives us the inner product, which is just a measure of how much 2 states overlap. And, of course, the normalization condition dictates that our probabilities must always, without fail, sum to exactly 1. Looking at the block sphere, it is critical to remember the difference between our angles. The polar angle, theta, controls the physical mix of the 0 and 1 states, but the azimuthal angle, phi, is the relative phase. That relative phase is entirely invisible to basic measurement probabilities, but it is absolute magic for creating interference effects. And interference is the true engine that makes quantum computation work. Bringing it all together with the postulates, cloning, and coding, let's anchor these abstract rules of quantum mechanics to a strict, persistent color logic so they stay firmly in our memory. Let's map out our colors. Teal represents postulate 2, reversible unitary evolution. This is how closed systems behave, preserving all probabilities. Amber represents postulate 3, that sudden, probabilistic, and irreversible collapse that happens the moment we make a measurement. And violet represents postulate 4, the tensor product of composite systems, which is the exact literal mathematical foundation that makes entanglement possible. These rules brilliantly illustrate 2 mirrored consequences in quantum mechanics. On one side, the no-cloning theorem ensures ultimate security for quantum key distribution, but the trade-off is that protocols like teleportation are forced to destroy their original state to work. Then, looking at its mirror image, super dense coding allows us to send incredibly dense classical data over a single quantum channel. Now watch out for the classic exam trap when it comes to super dense coding. Yes, Alice sends 2 classical bits of information by transmitting only 1 physical qubit, but this is perfectly bound by the laws of physics. It is not faster than light communication. Why? Because Bob physically cannot recover those 2 classical bits until he receives Alice's 1 physically transmitted qubit to complete the measurement. The entanglement alone carries absolutely no signal. As we wrap up today's explainer, I want to leave you with a thought to chew on. Teleportation sends 1 qubit using 2 classical bits. Super dense coding does the exact reverse. It sends 2 classical bits using just 1 qubit. If quantum mechanics allows us to take a hard constraint like teleportation and perfectly invert it into an incredible feature like super dense coding, what other physical impossibilities in the universe are really just features we haven't reverse engineered yet?